So, okay. So we've agreed that the filter that we have used for the filter that we had yesterday, which was basically a resistor and a capacitor, where you're putting the input in here and getting the output from there. Okay, this is what we call a low-pass filter, and we'll talk about how to change it to a high-pass filter. In fact, changing it to a high-pass filter is quite simple. Okay, but anyway, this is called a low-pass filter. What is the meaning of a low-pass filter? It means that putting low frequencies, it's a low pass, so it passes low frequencies. You put signals with low frequencies, they'll pass. You put signals with high frequencies, they'll be rejected. They'll be filtered out. This is why it's called a filter. It's like the filter that you, if you are one of those who drink coffee a lot, sometimes when you want to do coffee, you put a filter, which basically will prevent some of the, the grains of coffee and so on from passing. A filter is exactly the same, except that that one is a coffee filter. This one is an electric filter. It filters electric signals. So what does that filter do? If you put low frequency, for example, if I put DC, okay, let me take several examples. If I put DC, this is the input. The DC will pass without any attenuation at all. Okay, if you put 5 volts DC, the output will become 5 volt DC. If you put low frequency, for example, a cosine that looks like this, this is also considered to be low frequency. The output will probably be almost the same. Maybe not exactly the same, but very close to it. Okay? Now increase the frequency of the input. What happens to the output? The output will be a copy of it, except that maybe a shifted version copy of it, okay? Except that it will be attenuated. You see that the output now will look like exactly the same shape, but attenuated. Okay? Put even a much higher frequency, something like this, for example. Okay? You might find that the output is almost zero, something like this. Sorry for the plot, but it should be a cosine, but with very low amplitude. I'm sorry, my sketch is not appropriate, but it should be exactly a copy of the input, but with significantly attenuated amplitude. Okay, put a much higher frequency, something like this. You may end up with almost nothing at the output. Basically, this means that the signal has been completely attenuated, completely killed. In fact, usually low-pass filters, gentlemen, are sketched, or what we call the magnitude response, and I think I talked about the magnitude response some time ago. The magnitude response of a low-pass filter usually shows this. This is the frequency. It shows you that at low frequencies, this is zero frequency. This is, for example, 1 hertz or 1 radians, 2 radians, 3 radians, and so on. As you increase the frequency, what happens? The magnitude response drops to 0. It basically indicates put low frequencies, the output is exactly the same. Put a little bit higher frequency, the output may be slightly attenuated. Higher frequency, attenuated more. Higher frequency, attenuated more. Higher frequency, attenuated more. And at the end, if you put extremely high frequency, the signal is completely eliminated. By the way, filters are used in all, not some, but all communication systems. You cannot have a communication system without filters. In fact, filters are one of the most fundamental components in any communication system. Not only communication systems, but communication systems are very well known in using filters. Okay? So your mobile phone, the mobile phone that you have, since it's a communication system, it has, I can tell you, at least 10 filters, 20, 50 filters. I don't know how many, but you have filters for different things that are used. In fact, you have a filter for the Wi-Fi. Multiple filters, in fact, not only one. You have filters for the 3G or 4G, filters for the 3G, filters for the 4G, filters for all types of communication, for the Bluetooth and so on. All communication systems are based on user filters. When you take communication, you'll understand why we need filters. Okay? But this is the basic concept of filters. Now, I took that signal, okay, the blue one, and I put it into that filter. Okay? Simulated, basically, and what I'm doing is I'm simulating the effect of that filter to produce to you the red. And then I'm slowly increasing the frequencies of, basically I'm reducing the period of this signal. See the signal? Or basically, you see, remember that T0 in there, or in here, okay? This is what we call T0, and omega 0 was equal to 2 pi over T0. Okay. What I'm doing, gentlemen, is I'm increasing the frequency, meaning I'm reducing the period. I'm making the signal, instead of being like this, I'm kind of compressing it in time. Yani putting a signal that looks like this now. Yeah. And so on. Okay. So I'm increasing the frequency. I'm compressing it in time. If you compress a signal in time, you increase its frequency. And instead of the period being 10 or 20, now the period is only 2, or the period is 0.1, and so on. As you increase the frequency of that signal, omega 0 increases, okay, which means that the different components. You remember the spectrum that what we call the magnitude spectrum. Okay. Sorry. My apologies. What I was doing is I was reducing the frequency. Sorry. My apologies. I was reducing the frequency, basically making this wider. Okay. My apologies. Making it. Sorry. Make it. Hold on. Just give me a minute. If I make this narrower. It's okay. It's okay. Yeah. I was increasing the frequency. My apologies for this. Okay. So I was increasing the frequency. Now, if you increase the frequencies of the signal, remember that this is omega 0, this is 2 omega 0, 3 omega 0, and so on. If you increase the frequency of the signal, omega 0 moves to the right, and 2 omega 0 also moves to the right, and 3 omega 0 moves to the right. However, I'm putting the same signal through the same filter. If the frequency is low, if omega 0 is relatively speaking low, you see, for example, that this is the filter. The filters are always plotted on both sides. But if I put a signal with, relatively speaking, low frequency, the fundamental frequency is low, this means that this is the frequency, this is the amplitude spectrum of the signal. Something like this. Okay? So most of the components of the signal that have some value fall within what we call the pass band of the filter. This is the region of the filter in which it passes most of the signal power is called the pass band. The region in which let's say it stops most of the components is called the stop band, and there's usually a region between those which is called the transition region. But anyway, without going into detail, I want you to understand that a low pass filter will pass signals in a specific frequency, and let's say we'll try to reject the frequencies in higher frequencies. If you put a signal with low frequency, most of the signal components, the Fourier series coefficients, or let's say the Fourier series components of that signal, have low frequencies, so they fall within the pass band, which means that at the output of the filter, I get almost the same as the input. Yani this filter did not reject anything. It passed everything. But once you make those wider, or basically you increase the frequency of them, meaning instead of the previous figure, I have a figure that looks like this. So I increased omega 0 now compared to the previous case. Yeah. So now some of the components will fall outside the region in which the filter will pass. So what does the filter do? It kills them. It removes them. Once the filter removes them, the output of the filter is no longer similar to the input of the filter, but kind of a filtered version of it. And this is basically what I'm doing in here. Let me show you. Now, in this situation, almost all of the components of the input are passed. As you see, the difference between the output, which is the red and the blue, and the input, which is the blue, is very negligible. It's just very, very high frequencies here. Just a little bit of, if I just zoom in here just to show you. Let me zoom in there. And I'll show you that there are some differences, but the differences are not severe. Let me just zoom in here. You see, there is some difference. I'm not saying that they're identical, okay? But the difference is quite small. Okay? Now let's increase the frequency. And as I mentioned, what I'm doing is I'm increasing the frequency. Okay? And each time I increase the frequency, I'm pausing. Okay? Notice in here, there's as I increase the frequency, the change or the difference between the output and the input has increased. Let me just zoom in now and show you. Now you see, relatively speaking, significantly bigger change. As you see, there's a bigger change because I have filtered some of the components of that signal. Do it more. I'm pressing on the space, and I'm basically continuing further. Oh, my apologies. Let me just take this thing and put it to the bottom there so that it doesn't bother us. Okay? Look, what happens as I increase the frequency more components of the signal are being filtered by the filter. And you notice now that the output is not equal to the input. It approximates the input. However, it's not perfectly approximating it because I have removed some of those components. Do it more. And you see that the output eventually will be kind of a, I don't know. In fact, let me do something. If I remove, just give me a minute. If I remove the pause, that pause in there, okay? If I remove it and just increase the frequency there, 0.03, for example, okay? And let me run it. Let me just close this. Let me run it, and you see it slowly changing. It is happening slowly, okay? But eventually, you see that the signal becomes kind of a hugely distorted version of the input. Sorry, I changed the resolution there to 0.03, so I made it slower. It was I think maybe I should have left it at the original value. But anyway, just wanted to see slowly how removing more components affects the shape of the signal. Okay? So now, how were we able to do this? We were able to do it only because of the fact that we have the Fourier series. Without the Fourier series, we wouldn't have been able to do that analysis for that signal. Okay, Juan? But anyway, maybe I'll just speed it up a little bit so that you can see. There you go. Let's see, clearer maybe. Good. Now it's faster. There is one thing that I want you to notice in here. I cannot pause it, but let it just stop. Notice this is the input, the blue, and the red is the output. Notice where does the input, let's say, or the output, where does it was decreasing in here. I don't know if you can see what I'm pointing, okay? It was decreasing in here. Where did it start increasing? Only when the input signal increased. This tells you that this filter is a causal filter. The output changed as a response to a change in the input. If you see in a filter where the output starts dropping and before the input starts increasing, the output starts increasing. And if I have the red curve shifted a little bit to the left, this means that the system is not causal because the output changes before the input actually comes. Notice also, when does the output start dropping? It starts dropping when the input goes from 1 volt or whatever back to 0. Okay, Juan? Like, any question on what I just mentioned, gentlemen? So hopefully this will give you a clearer understanding of the Fourier series and how we can use it. Right. So let me close this and let me go now to the next topic. It's still running because this way. So let me close that. Okay. So now let me go to the lecture notes again. And now we'll come to something that is, this is something that you haven't seen before, and it's called the Fourier transform. Fourier transform. Okay? Now, what's Fourier transform? It's another tool. Is it similar to the Fourier series? And the answer is yes. It's somehow related to the Fourier series. Okay, but it's another tool that will allow us to analyze systems. Let's say. Okay, and if I have an input like what we've done with the Fourier series, if I have an input which is periodic, I can find its Fourier series, determine what is the frequency response or the what we call the amplitude response of the filter or of the system, and based on this I can find what the output of the system will be. The Fourier transform will also do the same, except that it will work on different signals. Remember, what type of signals was the Fourier series able to represent? You remember? We said that there must be a feature in any signal that the Fourier series represents. It has to be, تفضل محمد. Periodic. عليك نور. Okay. Any signal that you want to represent using the Fourier series has to be periodic. Now, one of you, I don't know, maybe none of you thought about this, but what if I have a signal that is not periodic, just for the sake of argument? For example, assume that I have a signal that looks like this, and then it's zero everywhere else. It's not repeating. And clearly, this signal is periodic. Okay. While the upper one, if there are no periods like this repeating, then it's not periodic. What if I took this signal, and this is one of the things that I was maybe trying to avoid to mention, but I'll mention it here because I think it gives you better understanding of the difference between the Fourier series and Fourier transform. If I have a signal that is not periodic, and I thought, well, okay, the Fourier series represents periodic signals, but it doesn't prevent me from thinking of a signal that is not periodic as being, what I'm trying to say is, what if I thought of this signal as being periodic and went and plugged it into the Fourier series where I thought of this as T0, okay? Or maybe this from here to here as T0. Okay? What if I think of a signal that is not periodic as it's having a period? It clearly doesn't repeat, okay? But what if I thought of it as having a period which is equal to T0, something like that? Let me erase the bigger one. Okay? Right? And went and plugged it in the Fourier series anyway, and tried to find its coefficients, and then tried to plot the Fourier series expansion of it. Do you know what the Fourier series will tell you? The Fourier series does not know that your signal was not periodic. It says that, okay, you have plugged into me a signal that looks like this, and you have told me what is the period, T0. You remember that in the Fourier series, we have to integrate over T0. And you have to even tell me what is omega 0. Omega 0 was equal to 2 pi divided by T0. So if you give me all of those quantities, I don't know. I'm acting as if I'm the Fourier series. I don't know whether you are giving me a periodic signal or non-periodic signal. So after you get the Fourier series coefficients, if you try to plot the Fourier series expansion of that signal, do you know what will happen? The Fourier series thinks that you have represented a periodic signal. It will basically show you a signal that looks like this in this interval. It's exactly the same. Outside this interval, what it will do is it will take this thing and just repeat it. Again and again. So it will repeat it infinitely. If you remember the application that I ran, the application that I told you that I developed many years ago, initially in the examples that I showed you when you put a specific shape. I don't know if, unfortunately, I closed MATLAB now, and it's going to take a while to run. But at the beginning, when I showed you the first examples, when we talked about the Fourier series, in fact, what I plugged into the Fourier series was an unperiodic signal, but told MATLAB exactly this, that I want you to think of this as being a periodic signal between, for example, -1 second and 1 second. And what the Fourier series expansion did is, when I plotted the Fourier series expansion, it plotted to me the signal in that interval between -1 and 1, exactly the same. But outside this range, it plotted other intervals, thinking that, you must have put into me a periodic signal. So if you don't have a periodic signal that you're putting into the Fourier series, unfortunately, the Fourier series will always assume that it's periodic. What if I have a non-periodic signal that I'm putting into that low-pass filter? Unfortunately, non-periodic signals will behave differently than periodic signals. I cannot say, well, let me look at the output. The output, for example, due to the periodic signal, for example, will look like this. Okay? So if I put only one period of that signal into the Fourier series, okay, let me think of the output of that filter being only one period. No, it doesn't work this way. It will probably be close to that, but because other periods in here, trust me on this, each period in there that, let me say it this way. This, when I put it into the filter, it produced an output that doesn't only limit to this region. In fact, the output due to this period of the input of the filter okay, probably will extend even over other periods. So basically, the outputs of the different periods get mixed together. So if you remove all of the periods and leave only one of them, unfortunately, this is not going to be equal to the output due to a single input. And let me just explain it to you this way. If you put periodic signal into a filter, okay, you get periodic output. Okay. Now, if you take only one period, okay, put it into the same filter, okay, the output, you cannot say in here, take only one period. And if I write in here, take only one period, okay, I cannot take one period from here okay, and put it in here. Let's say this is y of t, okay. I cannot do this. You cannot just take one period from the output of the system when you put into it a periodic signal and think that if I take only one period of the input, this will correspond to one period. Unfortunately not. Okay. If this was possible, yes, you would be able to use the Fourier series. We do not need the Fourier transform. But the problem is that we cannot use this, so forget about it. In some situations, yes, you can to some degree get accurate results. And in fact, unfortunately, I closed the MATLAB. You remember at the beginning, well, I think it's worth it. Sorry, I forgot, because I was not thinking that I'll explain it this way, so I didn't think that I needed MATLAB. Hopefully, MATLAB is not going to take too much to run now, because usually the second time you run it, it's slower. I mean, it's faster. Hopefully, because it's important that you understand this concept so that you know where do we or why do we need the Fourier transform. So it ran. That wasn't too bad. Okay. Let me open that document again. Not document. Open. Let me put a pause here. And I'll explain it to you. Hopefully you'll understand. I'll add, by the way, most of the stuff that I talk about, I added in the lecture notes. And let me make this just one. And I want it to run in large steps. Okay, so I've ran it. Now, in this situation here, what do you notice? This is basically the explanation of what I've just mentioned. Look at the input. By the way, let me also do a small modification. I want to do a small modification to the MATLAB code. Here, let me make them 500 or maybe 1,000 here. I hope that it doesn't take too much. By the way, trust me, if you understand what I mentioned sometimes as comments or so, believe me, Wallah, your life is going to be significantly easier because when you take other courses, you'll know what is going on. The problem with sometimes some students, they think that those concepts are not that important. All I need to know is how to solve, for example. Okay? But with those concepts, your life is going to become significantly easier because when you go to the lab, you'll understand exactly what is going on. Look, what I did is I increased the Fourier series coefficients. This is why, if you notice now, I have a more accurate figure compared to the input signal. Now, notice in here, let me zoom in. Just before, look, this is one period. The middle one is one period. The left one is another period, and the right one is another period. Let me look just before the middle period. Let me just look at the signal. Let me zoom in and look in there. What do you notice? If you notice that the signal is quite small, okay? The signal, the input signal is very, very small, okay? The blue one, right? The red one is almost zero because higher frequencies have been eliminated, okay? But look at the blue one. the blue one has almost been completely filtered out. Yeah, by the time, what I mean is, by the time the next period came, think of the left period as number 1, middle period number 2, right period number 3. By the time period number 2 has come, period number 1 has completely died. Okay? Now, if I cut in this situation, if I tell you, for example, what is the output of that system if I only put one period? Yes, you can say because each period, the effect of a period, for example, only extends over a specific region. Let me say zoom out. Let me do zoom out in here. Okay. Unfortunately, I cannot. Okay, let me print screen and take it to OneNote so that I can explain it in here. Nothing. Again, print screen. Okay, the functions are expressed. Print screen. Now it should work. Let's basically the figure. Okay. Notice what happens in here, gentlemen. As I put this input in here, let's be small so that I can have thicker line. As this period comes and gets fed to that system, the system responds to it. It provides you with an output. Now, what happens to the output? The output maybe fluctuates a little bit, and then it becomes 0. So by the time the next period comes, okay, the output due to the first period has completely become equal to 0. So I know that the output due to this period now, the red line that I see there, is only because of the second period that I put. And the output due to the third period that I put is only due to the third input period, and so on. In a situation like this, you can say that, okay, if I go to that figure that I sketched, in here, if I come, this is true. I can take one period of the input. If I have a signal that is not periodic, I can think of it as periodic, get the outputs of that system as a periodic signal, and then extract only one period of it, and this becomes the output due to a single period that I put at the input. In this situation, it works. However, if I come to the MATLAB code and press on the space, basically, down again, press on the space, notice what happens in here. The effect of the first period starts extending. If you notice in here, around 2 or so, the effect, the output due to the middle period is starting to go towards the third period, and the output due to the second period is starting to go towards the first period, and so on. Each output is, or let's say, the effect of each period is going towards the next period. If I continue, this effect is becoming even more severe. Look now. Let me even go a little bit more so that you'll understand the concept. Now, let's say that I have this situation here. This is the system that I have. Let me print screen. And let me come in here and paste this. Now, look in here. Can I say that this shape in here, you see this shape in here? Let me just make it thicker, maybe yellow. Here. Can I say that? There. Can I say that this shape, gentlemen, in here until this place, is only due to this input? What do you think? Or is there some residual, let's say some remaining part from the previous period in here? Look, this is the previous period, and it produced to me this output. Now, the output did not die completely at this point in here. What happened? A little bit remained. Okay? So, in fact, the output due to this output in here that I'm going to color now in orange is mostly due to this period, but also part of it is due to the previous period. So I cannot just extract one period from the output and say that this period correspond. If I just put one period at the input, the output is going to be equal to one period of the output. No, I cannot do it in this situation. So in this situation, this is no longer valid. In general, it's no longer valid. Only in specific situations. If the periods are very far away from each other, yes, this is true. If the periods are close to each other, relatively speaking, then this cannot be used. What is the other tool that I have to use? I have to use the Fourier transform. Okay, so now this is basically the main concept of the Fourier transform. The Fourier transform is to represent signals that are not periodic. Now, also the Fourier series, trust me, it can also represent periodic signals, because you can always think of, yeah, let me say this way, you can always think of a periodic signal as a non-periodic signal. And if someone says, I have this signal in here, is this periodic? You're going to say no, yes. Then what if someone said, well, I cannot see that it is periodic. It's a signal that has three, or let's say, or maybe even infinite of those periods. Okay? And yeah, what I'm trying to say, gentlemen, is that sometimes you can also think of a periodic signal as being non-periodic. So the Fourier series will also be able to represent periodic signals. Okay? But the main purpose of using Fourier series is for non-periodic signals. Okay, now let's look at the concept of the Fourier series. Where does the concept of the Fourier series come from? And this is basically the material that I have at the bottom there. When we started talking about the Fourier transform. Now, if you don't understand everything that I'm going to say now, don't worry about it. I mean, this is just theory. I have to mention it, but if you don't understand it, don't worry about it. Okay? Let's say that we have a signal that is periodic, and I'm calling it in here x of t0, because I want to distinguish between x of t0 and x of t. X of t0 evaluated at small t, evaluated at small t, and x of t. Now we're interested in non-periodic signals, but to show you what is the Fourier transform, let me start with the Fourier series. And those are the two equations that we have learned, yeah, for the Fourier series. Okay, the first signal, or I'm sorry, the first equation basically tells us what is the representation of any periodic signal. X of capital T0 is a periodic signal here. Okay? Think of it as a periodic signal. So x of t0 is equal to the sum from k equal minus infinity to infinity of the ck's, which are the Fourier series coefficients, multiplied by e to the power of k omega 0 t. This is exactly the same formula that we have above. I didn't modify anything in it. I just called the signal, instead of calling it x of t, I called it x of t0 to indicate that we're talking about a periodic signal. And this periodic signal has a period that is equal to t0. Okay? And t0 is basically equal to 2 pi over omega 0. In fact, it's written there. Okay? So think of this as a periodic signal. And this is how we get the Fourier series coefficients. Okay? C of k is equal to 1 over t0, the integration over 1 complete t0, x of that signal, and that signal multiplied by e to the power of minus j k omega 0 t dt. Those are the two equations that we learned above. As I mentioned, the only difference is I wrote x of t0 there instead of x. Right. Now, let us, just for the sake of argument, let's think of t0 there. The integration there is over one period. So I can take the integration to be from 0 to capital T0, or I can take it to be any point plus T0. You remember, this is what we mentioned when we talked about the Fourier series. You need to integrate over one complete period. It doesn't make any difference where you start and where you end. So just for simplicity, I'll assume that we're starting the integration from minus T0 over 2 to T0 over 2. So 1/2 period before 0 and 1/2 period after T0. Okay? Right. Now, let me say that this is my signal. Let me erase this stuff in here, and let me sketch a signal. Let me erase this. Let's say that my x of t0 evaluated at small t looks like this. Just a signal, a signal, periodic signal, where the distance between here and here is t0. Okay, so it's a periodic signal. And this repeats in there and repeats in here. Yeah? It's a periodic signal with a period that is equal to T0. Let's just think, imagine that what I did is I kept the shape of the signal from minus T0 over 2 to T0 over 2. Okay, I kept the shape of the signal exactly the same. Okay, but I separated those periods. And think of it as I have added 0 in here. Yeah, I have extended I've taken those periods and moved them away from each other. So what am I doing? The shape is exactly the same. I'm not changing the shape. I'm not expanding the signal or compressing the signal. All I'm doing is I'm taking those periods and moving them away. So basically, I'll end up with a signal that looks like this. Exactly the same shape in here. This is exactly the same shape, but I have moved it away. This is exactly the same shape, but I have moved it away. Okay? So I'm making T0 increase. Now, this is basically the new T0 over 2. And this is the new minus T0 over 2. And so on. I keep doing this. So I'm slowly increasing T0 so that I separate those periods from each other. So assume that this is what I'm doing. Now, if I do this, gentlemen, okay, I just need to maybe point out a couple of things. If you look at this in here, okay, in this we have K omega 0 in here, and we have 1 over T0 there, and we're integrating over a period that is equal to T0. As capital T0 reaches infinity, it becomes basically, and you're increasing the period and making it almost equal to, I'll come to your question, but just give me a minute, okay? As you increase the period and make it approach infinity, what happens to the integration? The integration becomes the integration from minus infinity to infinity, because remember, I was integrating over one complete period, and that complete period was from minus T0 over 2 to T0 over 2. If you set T0 to become equal to infinity, the integration becomes from minus infinity to infinity, okay? This is number one. And the second point is I have also K omega 0. Now, if T0 increases and approaches infinity, and in the limit as T0 approach infinity, okay, what happens to K omega 0? Omega 0, remember that it was equal to, omega 0 was equal to 2 pi over T0. Sorry, let me, okay, this is equal to the limit of K 2 pi over T0, okay? Trust me on this. Once T0 approaches infinity, K multiplied by 2 pi, okay, I can rename it without going into detail and how I'm doing this, but I can rename this into a different quantity that I'm going to call omega. Yeah, basically think of this as a frequency. As T0 approach infinity, okay, this quantity, the whole quantity here, approach 0. Okay, I'm sorry, not the whole quantity, but this quantity approach 0. If you have a quantity that is approaching 0 and you multiply it by an integer k, where k is equal to 1, 2, 3, and so on, you can simulate this, or you can rename this quantity to be equal to a different frequency. Now, the difference between omega 0 and omega is that omega 0 is just a constant. It was equal to 2 pi over, for example, 5 or over 7. While omega there is equal to a variable. Where does the variable come from? It comes from the fact that k takes values that are from 0 all the way to infinity. Okay? Yani I don't know if maybe a better way of explaining it, but all I want you to understand is that this quantity now, I can call it omega. So in fact, in this relationship in here, I'll end up with, where is it? Or let me take this relationship in here. This integration here becomes the integration from minus infinity to infinity, okay? X of T0 now was a periodic signal. Once I set T0 to become equal to infinity, the signal becomes no longer periodic. I mean, it has one period at the location of 0. Where does the second period happen? It happens at infinity. And a period which has its second period happening at infinity is basically not a periodic signal. So I can rename this to become X of T, where X of T is not a periodic signal. And the e to the power of jk omega 0 t becomes e to the power of minus j omega t dt. Okay? And the last part is this quantity here, T0 multiplied by ck. Okay? Okay. T0 multiplied by ck, I can rename those as capital X of omega. Without going into detail, all I want you to understand, gentlemen, is that there are some modifications that I can do to the Fourier series coefficients to change this formula from this formula, which allows me to find the Fourier series coefficients, into a formula that looks like the following. Yeah. Now, what is this? This thing is nothing but what we call the Fourier transform. I'm sure that probably you didn't understand everything that I mentioned before. Okay, and I'll try to explain it well. I copied this material from an old material that I had, so I didn't have the time, and I did it last night, very late last night. Well, I think I went to bed at 1 p.m., so I didn't have the time to write all of the details. But I promise you that once I upload the updated lecture notes, you'll have complete detail of how did I transform the Fourier series into Fourier transform. Okay? The Fourier transform basically says this, that you can take any signal that is not periodic, x of t, okay, multiplied by e to the power of minus j omega t, integrate it with respect to t. Since I have two variables in there, I have omega and I have t, and I'm integrating with respect to t, the output will always be a function of omega. And that function of omega, I'll call it capital X. Why is it called capital X? Because the input signal is small x. So the Fourier transform of a signal x of t is always capital X of omega. And you see that this capital X of omega has very important use in systems. Okay? So the Fourier transform of x of t is obtained using this formula, and it provides me with another signal that is called x of omega. Now let me, maybe in the next 12 minutes or 30 minutes or so, let me explain to you what is the meaning of x of omega. Okay? Now, all of us know how to plot a signal. If I give you a signal, for example, if I tell you plot a sine, you will go and sketch the sine this way. This is the sine. Without even thinking about it, what is the x-axis? What is the x-axis whenever I plot a signal? Any ideas? Any thoughts? When you plot a signal, for the signals that we have talked about, it's time, exactly. Okay, so this is time. Okay, now think of time as one dimension. Okay, the other dimension that corresponds, let's say that is, I don't know if I can use this term appropriately here or not, but we live, we live in a world in which time is, I don't want to say something and I regret it. Maybe it's inappropriate. I mean, maybe it's not accurate. I mean, there's nothing in what I'm going to say that is bad or so. But I'm just afraid that I say something and then it becomes completely meaningless or so. We live in a world, gentlemen, where every second, 1 second of your life passes. Right? You can think of your life not versus time, but you can think also of your life or any signal that we have. You can always plot any signal or any activity that happens, not versus time, but you can also plot it versus frequency. Now, the human beings were used to using time. If I tell you, for example, now something happened, after 1 hour, something else will happen. So I can plot those two activities versus on the line of, let's say, on the time axis. And I can put, for example, that this is the time at which the first event happened, and this is the other time at which the other event happened. But equally, you can also represent everything that happens in life, not versus time, but versus frequency. Meaning any signal, like the sine that I have, I can plot it again versus frequency. Now, if you plot it versus, it would be that you take that signal and just do something like this. Okay, and put in here F. No, this is not what I'm saying. To plot any signal versus frequency, you have to take that time signal and transform it from one domain, which is the time domain, into the frequency domain. How do you transform a signal from time domain to frequency domain? It's using that Fourier transform. The Fourier series was doing something like this, but it was only doing it for periodic signals. It showed us what is the spectrum of the signal, where do the different components of the signal exist. You remember the spectrum of the signal? Okay, those vertical lines that are sketched, okay? Those represent what frequencies does the signal have, what components does the signal have, and at what frequencies. Now, if the signal is not periodic, then you end up with the way for finding the spectrum or what are the different frequency components that the signal have. You cannot use the Fourier series. You have to use the Fourier transform. Okay, Juan? So the Fourier transform is a way for representing signals in frequency. Okay, until now, I think Bedr, I think you had a question. Sorry, it was maybe 10 minutes ago, but if you still have the question, please ask. Anybody else has any question? Bedr, you still have the question? I see you still raising your hand. Okay, no problem. Okay, so this is basically the concept of the Fourier transform, gentlemen. Okay, have you seen an oscilloscope, by the way, or not? I don't know. Problem. I'm not sure. I've seen an oscilloscope. Have you seen an oscilloscope? You haven't seen an oscilloscope, probably, because I think the first course in which you start to see an oscilloscope basically is a device that electrical engineers usually use, typically in the lab, to plot for you signals versus time. Let me show you basically what an oscilloscope is. If I come here and write oscilloscope. Okay. And put images. This is basically an oscilloscope. And the oscilloscope, gentlemen, is there are kind of sophisticated let me just tell you something. I remember when I was a student, when I first used the oscilloscope, honestly, I fell in love with it. Why? You can put a signal and it shows you the signal, plots the signal. You can put a voltage and shows you the plot of that signal versus time. This is an oscilloscope. Okay? And the axis in here, I don't know if I cannot mark, okay? But the x-axis there is basically time. Right? The x-axis is time. Now, when I was a student, I honestly, when I first used an oscilloscope, trust me, I fell in love with it. Okay, to the point that I was thinking when I was still in KPP, maybe the third year or so, maybe I need to buy an oscilloscope. At that time, by the way, buying any equipment like this was not easy. Why? Because there are not many places in here in the kingdom that can sell this, and you cannot buy stuff easily from outside. Nowadays, it's quite easy. And the third reason was that oscilloscopes at the time were quite expensive for my budget. I remember that I think I went to one of the places that have oscilloscopes, and they told me I think that a typical oscilloscope would cost something like 6,000-7,000 riyals. On a budget where I was receiving only 1,000 riyals, that's something like 6 months or 7 months budget. Okay, so clearly it was out of the question. But I promised myself that inshallah when I graduate and I have an income, I'll buy an oscilloscope. Now, after a while, I took other courses in which I learned that there's, by the way, later, now if you try to buy an oscilloscope like this will probably cost you 2,000 riyals, or maybe even cheaper. You can buy very good oscilloscopes that are quite cheap. Why? Because the technology has changed. The number of companies that sell oscilloscopes is significantly larger, okay? And many of those oscilloscopes now, in fact, you can even have an oscilloscope on your computer now. You can buy a simple device that you can connect to your computer, and you don't need a display. Basically, your computer becomes a display. So oscilloscopes now are quite cheap. In fact, just a few months ago, I was thinking of buying an oscilloscope. By the way, I never bought an oscilloscope. Now, my salary is much higher, okay? But I never bought an oscilloscope, okay? I don't know what happened. I think I went for the PhD and I forgot about this. But the point is, the oscilloscopes are one type of devices that plot the signal versus time. I learned later in other courses, I think in communication course, that there's another device that will almost do the same thing, but instead of having the x-axis being time, the x-axis is basically frequency. And that device is not called an oscilloscope, it's called the spectrum analyzer. Now, at that time, when I saw the spectrum analyzer, I also fell in love with the spectrum analyzer. By the way, I always fall in love with electric equipment. So I fell in love with the spectrum analyzer, and I wanted to buy one. Again, okay? I thought maybe, an oscilloscope is kind of low grade. Let me go to the sophisticated device, which is a spectrum analyzer. And typically, by the way, an oscilloscope has its own uses. A spectrum analyzer has its other uses in electrical engineering. And I was shocked to know that spectrum analyzers, especially a long time ago, if an oscilloscope costs about 5,000 riyals, a typical spectrum analyzer will cost 50,000 riyals. Now, they look almost the same, by the way. If I show you in here, look, this is an oscilloscope, right? Those are pictures of oscilloscopes. Let me write in here spectrum analyzers. You see almost the same shapes. Okay. Now, clearly, what's inside is different. Okay? What's inside, the plot that is inside is completely different. Look, this is a typical signal that you see, for example, in a spectrum analyzer. Let me look at this. By the way, you see this company, RS? This is a company that has a branch here. Okay? I don't know what RS stands for, but it's a company that has a branch here. And I have visited this company multiple times. One of them, in fact, to buy an oscilloscope, to buy the oscilloscope. Okay, but as I mentioned, at the time it was too expensive. Okay. Now, what's the difference between the signal that you see in here and the signals that we saw in the oscilloscopes? In the oscilloscopes, it was versus time. This spectrum analyzer will read the signal again versus time, but will take its Fourier transform and convert it into the signal that you see in front of you here. That process of converting the signal from time to frequency is the thing that causes this device to change its, or let's say to have its price change from 5,000 riyals to about 50,000 riyals. Now, spectrum analyzers also have dropped in cost. Now you can buy a decent spectrum analyzer for about 5,000 riyals or 6,000 riyals or so. But typically, spectrum analyzers, good spectrum analyzers, will cost more than oscilloscopes. Why? The answer is simple. It's because the oscilloscope plus versus time, as the signal comes versus time, it just plots it on the screen. The spectrum analyzer will have to take the signal and multiply it by that complex exponential mathematically, okay, and integrate it. And this process is not easy to do in a computer. I'm not saying it's too complicated. You can do it, but it requires sophisticated, let's say, calculations to do it appropriately. And this is why calculating or plotting x of omega significantly costs more money than plotting x of t. Okay, Juan? Right. So what is x of omega, as I mentioned? It's the spectrum. It basically tells you what are the contents of the signal versus frequency. If I plot, as you see inshallah later, if you plot, or let's say if you have a signal, and I'll talk, inshallah, in more detail about the Fourier transform later, okay? But just for your information, if you have a signal that looks like a cosine, for example. I don't expect you, by the way, to know the answer to this question that I'm going to ask. But if you have an oscilloscope that is showing you a cosine, what do you think the shape of the signal on the spectrum analyzer versus frequency? Anybody can guess what the shape will be? This is frequency, this is time. Give it a guess. What do you think the shape will be? تفضل جهاد.
بتكون الماgnitude بس يا دكتور.
Magnitude, yes, but how does it represent in you're absolutely right. يعني what you're saying is
lines
correct,
بس
okay?
زي delta functions.
Exactly. It will be a delta function. Okay? It will be a delta function. Thank you so much, Jihad. Very, very correct answer. Okay? In fact, it will be a delta function at what frequency? We'll see this inshallah later. Okay? At the frequency of this. Yeah, if this is, for example, is cosine, let's say 2 pi 5t. So this is omega. Okay? Let's say this is omega instead of f. Okay? This is omega. In fact, you see that the spectrum of that signal will be 2 deltas at 2 pi 5 and minus 2 pi 5. So it's in fact 2 deltas. You remember when we talked about the Fourier series, I think one of you asked me, why are we using cosines? Or at least, why are we using sines and cosines? And or maybe I commented to this, that we are using sines and cosines for a reason. Okay? This is exactly the reason. You see, a sine or a cosine function contains only a single frequency. A sine or a cosine is a signal that only contains a single frequency. Okay? A sine or a cosine only contains a single frequency. So when we represent a signal using sum of sines and cosines, we are basically saying what are the contents of that signal at that specific frequency, and at that specific frequency, and at that specific frequency. If we use in the Fourier series expansion, and we could have done this, if we use the signal that contains multiple frequencies, and for example, if we did the Fourier series expansion using another signal or another group of signals that are not sines or cosines, in which those components contain, each one of them contains multiple frequencies. This means that if I try to represent the signal in frequency domain, each signal, okay, will have to be, say, the different components will overlap with each other. What I mean by this is, if I have a signal and I'm trying to represent what, or trying to determine what are the frequency contents of that, I'll see, for example, that that signal has the addition of two components. Let's say two signals that each have multiple components. The first signal has, for example, 3 components in here, or 4 or 5 components, and the other signal has other components that may overlap. The spectrum becomes a complete mess. You're not going to be able to see what is the spectrum of that signal if you use other signals than the sine or cosine. This is why in the Fourier series we use the sine and cosine. Okay, so I'll stop at this point. I promise you, inshallah, later today I will give you that formula sheet, and I've thought, I've already put some functions there, and I'll scan over the lecture notes and find anything that may be useful to you. I'll plug it in that formula sheet, and I'll send it to you. Okay, Akhwan? And inshallah, as one of you suggested, maybe if you want tomorrow, I can give a problem session where I can solve some problems. Okay, Akhwan? Okay. I do not promise you 100%, but most likely I'll do it. Okay? If I don't have anything, tomorrow, inshallah, we'll do it. I'll give you more details, inshallah, tomorrow. Okay? So if you have any questions, ask. If you don't have any questions, inshallah, I'll see you tomorrow. Fadal, Muhammad.
Doctor, do you have an office hour today?
Yes, I do. If you have any questions, yes. In fact, from now to 2 p.m.
Okay. Thank you.
Okay?
Sure. On Teams or Blackboard?
On Teams. I think Teams is going to be easier. Okay? So if you want, I'll be available on Teams. Just give me a call or let me know. Give me a call. Okay? Just give me a call and I'll respond to you.